This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question AB5, namely the volume of a solid with known cross-sections. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. First, I'll provide a little background to this topic and what I think you need to know before solving these kinds of volume problems. Okay, the prerequisites. I'll talk about a general intuitive definition of volume, and then I'll use this idea to derive a formula for the volume of a solid with known cross-sections. And this will really be a general, all-purpose definition. I'll present and solve a few examples, and I'll leave a few for you to consider. There are often area volume problems on the free response portion of the AP Calculus exam, and many of these problems involve a part that asks for the volume of a solid with known cross-sections. So my objective here is to understand the formula for the volume of a solid with known cross-sections, where it came from and why it makes sense, and how to use this formula to find the volume of certain solids. Now, in order to solve these types of problems, well, at least in order to understand where the formula comes from, I think you need to know the definition of a definite integral in terms of a Riemann sum, and we'll use this concept to derive the formula. And then to solve some of these problems, you need to know and use the fundamental theorem of calculus. The problem of finding the volume of certain types of solids is similar, at least to me, to the problem of finding the area of regions in the plane. We have an intuitive idea of what volume means, but we need to be more precise by using calculus to provide an exact definition of volume. So let's start with a simple solid, a cylinder. Well, okay, a right cylinder, as shown in the figure. This cylinder is bounded below by a plane region B sub 1, called the base. It's bounded above by a congruent region B sub 2 in a parallel plane. And the cylinder consists of all points on line segments that are perpendicular to the base and join B1 to B2. So this is the shaded solid region in the figure. If the area of the base is A, and the height of the cylinder, the distance from B1 to B2 is h, then it seems very reasonable that the volume V of the cylinder is defined to be V is equal to A times h. Now, suppose the base is a circle with radius r. Then the cylinder is a right circular cylinder, and the area of the base is the area of a circle, pi r squared. And the volume of the cylinder is the area of the base times the height. So V is equal to pi r squared times h. And finally, if the base of the solid is a rectangle with length L and width W, then the cylinder is a rectangular box, also called a rectangular parallelepiped. But the volume is found in the same way. It's the area of the base, L times W, times the height, h. So the volume is L times W times h. Now these definitions of volume all seem pretty reasonable. But what if the solid S is not a cylinder? We'll use these ideas about volume and the usual calculus approach to solve this problem. We'll find a discrete approximation, and then find better and better approximations. We'll let n increase without bound. That is, we'll cut S into pieces, and we'll approximate each piece by a cylinder because we know the volume of a cylinder. We'll estimate the volume of S by adding up the volumes of all the cylinders. And then we'll find the exact volume of S through the familiar limiting process, in which the number of pieces becomes large. Let's see if we can put all this together and derive a general volume formula. Let's consider the solid S as shown in the figure. It's the blue shaded region. Pass a plane perpendicular to the x-axis through S, and consider the intersection of the plane and S, a plane region called the cross-section of S. Let A of x be the area of the cross-section of S in the plane p sub x. It's represented by the green shaded region in my figure. Think of slicing S through x and computing the area of this slice. This cross-sectional area A of x will vary as x increases from A to B. Let's continue and use these definitions to get an estimate of the volume of S. So divide the solid S into n slabs of equal width delta x. So a slab is like a thick slice. Think of slicing a loaf of bread. Choose points x sub I star in the interval x sub I minus 1 to x sub I, and approximate the volume of the ith slice s sub I by a cylinder with base area A of x sub I star and height delta x. Okay, it's a cylinder on its side. Well, we know the volume of this cylinder. It's the area of the base times the height. So the volume of the ith cylinder is A of x sub I star times delta x. And therefore the volume of the ith slice of the solid is approximately this value. So we can add the volume of all the slices and approximate the volume of the solid S by this sum. This approximation certainly seems to become better and better as n increases without bound, or as n goes off to infinity. Think of the slices or the cross-sections or the slabs as becoming thinner and thinner. Therefore, we define the volume as the limit of these sums as n goes to infinity. But this is the limit of a Riemann sum, and by definition, it's a definite integral. So here's our precise and very general definition of volume. Let's let S be a solid that lies between the lines x equal a and x equal b. If the cross-sectional area of S in the plane p sub x through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume of S is given by the limit of this sum. And we recognize this sum as a Riemann sum, and therefore this is a definition of a definite integral from a to b of a of x dx. Here's a little closer look at this definition. I think it's important to remember that a of x is the area of a moving cross-section obtained by slicing through S perpendicular to the x-axis. And if S happens to be a cylinder, the cross-sectional area is constant at any x. So that means that a of x is just plain a. And the volume, using the formula in our definition, is simply a times the difference, b minus a. And this agrees with our intuitive idea of volume, where v is equal to a times h. Let's try an example. Suppose the base of a solid S is a circle of radius 1. For this solid, the cross-sections perpendicular to the x-axis are squares. Find the volume of this solid. Well, I need a figure to help me visualize this solid, and especially the cross-sections. So let's position the circle in the xy plane centered at the origin. Now we could really put this anywhere in the plane, but this seems simple and convenient. We'll let p sub x be the plane that intersects the solid in a square. I'm searching for the area of this arbitrary cross-section, the intersection of p sub x and the solid S. In this figure, I can see that at x, the distance from the x-axis to the top of the circle is the square root of 1 minus x squared. So the length of a side of the square is twice this value. Therefore, a side of the square has length 2 times the square root of 1 minus x squared. Now, this is a rough idea of what I think this solid looks like. And maybe you can see how this fits on the top of the circle and the plane, and even see the cross sections. The area of a square is side squared. So here's an expression for a of x. Using our volume formula, we have this definite integral. And I can see that this integrand is an even function. Or I can use the symmetry in the solid to simplify the definite integral slightly. I can find 2 times the definite integral from 0 to 1. Use some basic anti-differentiation rules, then the fundamental theorem of calculus, and simplify. The exact volume of this solid is 16 divided by 3. And here's a quick technology solution. I defined the function a, the area of a cross-section at x. And I simply found the definite integral without any simplification in the expression. And the TI-Nspire, the CAS version, returns the exact symbolic answer. Here's one more example in which I will use technology to help visualize the cross-sections and to find the volume. The region R in the plane is bounded above by the graph of f, below by the graph of g, and on the left by the y-axis. For this solid, the cross-sections perpendicular to the x-axis are semicircles, with diameters that extend from y equal f of x to y equal g of x. Find the volume of this solid. Using the TI-Nspire, I first defined the functions f and g. Then, on a graph page, I tried to visualize the base of this solid. Here's the graph of f and the graph of g. Now, I was a little worried when I read this problem about the boundary of the base R on the right. But I can now see that these 2 graphs intersect near x equal 2. I found a good estimate of this point of intersection on the graph page, but I will confirm this on a calculator page in a minute. And I also drew in a diameter of the semicircle at an arbitrary value x. On a calculator page, I used the zeros function to find the x-coordinate of the point of intersection. And then I stored this value in the variable b. Next, I defined the function a of x, the area of a cross-section, here, the area of a semicircle. The radius of the semicircle is f of x minus g of x, that quantity, divided by 2. So the area of the semicircle is pi times this radius squared times 1/2. Then I just need to find the definite integral of a of x dx from 0 to b. And the volume of the solid S is approximately 0.246. And here are 2 more problems for you to try, and both of these involve the volume of a solid with known cross-sections. I would like to suggest that you sketch the region R in both cases. And you might even try to draw the 3-dimensional solid described. I hope this video provides some insight into finding the volume of a solid with known cross-sections, and provides a few AP Calculus type questions. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.